Hello everybody. So today we will talk about Ubuntu Core on RISC-V and how we enabled Ubuntu Core on RISC-V. So why Ubuntu on RISC-V? So why Ubuntu? Ubuntu is, we have 60 million community users. It's widely used all across the Linux spectrum. So we have 3 million developers all around the world, so Ubuntu is the #1 choice for the development. And what is Ubuntu Core? So it's optimized for the embedded deployment. So it's a lean version of Ubuntu. We have scaled down the version, so we are down to 200 megabytes the install package, or smaller if you go really some other embedded deployments like on ARM systems and so on. So it's fully containerized, so all the applications are running as a containers on it. We have out-of-box security baked in, so everything is running confined. All the applications are running confined, so you have your services, so you have to grant them permissions in order to execute their function. So you ensure that if there is a vulnerability in your application, it doesn't escape the confinement and cause more trouble in the system. So it's bulletproof updates, we have resilient updates, and it's certified Ubuntu, and there is a large ecosystem of applications into which we will get a bit later. So as Ubuntu has a known stable release cadence every 2 years, the same applies to Ubuntu Core. So we have 2 years release cadence, so every time you see Ubuntu LTS being released, being 18.04, 20.04, 22.04, there is also accompanied Ubuntu Core release. Those releases are having 10 years support baked in, so we have a 5-year standard support and optional 5 years extended support. So you get all total 10 years of support. That's for the kernel and also for your user space application and the system. Of course, that's all the security updates and so on. So now, here is a bit more about the architecture of Ubuntu Core. So you probably might be familiar with the standard Ubuntu server, Ubuntu desktop. It's a Debian-based system. So with Ubuntu Core, we rejig the system a bit more, so to be more prepared for the IoT deployment. So we have 4 main building blocks. We have a kernel snap, where we have a Linux kernel packaged as a snap. We have a gadget snap, so you can think of it of all your non-HLS components, so second stage bootloader, all other board-specific parts. You have a snap-d-snap, you can think of it as the brain of the operation, so that's a daemon which is orchestrating the life cycle of the device. And then you have a base snap, in our case could be Core 20, Core 22, and that's your minimal root file system. We're talking about 50 megabytes of a root file system. All the snaps are underneath a squashFS file system, compressed. And then you have on the top, you're running your confined applications. So the snaps then by design are read-only, so it's immutable package that you install on your system, and your writable data for your applications are separate of the application payload itself. And as you see, like they are nicely sandboxed from each other. So next thing we have. So it's full automatic unattended update experience on it. So out of the box, the system will every 6 hours check if there is an update, and it will automatically install the update if there is any update available. That applies to kernel, your gadget snap, or your root file system, as well as all the applications. So why they are unattended? Because the system has automatic healing. It's able to recover from failed updates. So we have an integration in the bootloader. So your if there is a new kernel or OS update, the system will download it, prepare the installation while the system is still running, and then triggers the reboot. The bootloader then goes through the environment variable and decides which kernel or OS to boot. If anything goes wrong, you have a hardware watchdog, something panicked, hanged. Once we get back to the bootloader, we will automatically roll back to the previous version. So really unattended self-healing. Now we have the same for the applications, just slightly more improved in a way that we have also writable data, that you can have a writable data per each application revision. So if you're installing new version of your application, you have an option to have your writable data for that current revision put aside. We do take a copy and you run a new version with a new copy, a snapshot of the data. Why do we do that? If your update breaks and you need to roll back, you're running your previous revision with your previous snapshot of the writable data. Think of migrating database. If you corrupted the database during the migration, no rollback will ever help you. Here, you have your previous copy of your database, so when you roll back, your chances that you're gonna have running system again are a lot higher. So, as an example, I'm running my home automation on it, and the system updates every 6 hours. If there is an update, I haven't touched it for months now. So, it's automatic, resilient, and really robust. So, the system is also secured, it's secure boot ready. So anything from the bootloader up, the boot is measured and we have chain of trust. So from the platform, all you need is a really hardware root of trust all the way up to the second stage bootloader. We have also baked in full disk encryption. So we have agnostic full disk encryption framework. We do support software encryption. We also support inline crypto engines if you have something like ICE encryption. And all it needs from the platform is a tiny hook which seals and unseals the keys. So if you have a trusted platform that allows you to sealing, unsealing keys, that's all you need to integrate with. And now we have a fully secured system. So secure boot and this encryption. Now, Ubuntu Core is also connected to our IoT App Store. So you have all the applications for thousands of applications, and there are coming more and more applications ready for RISC-V. So as an example, you have here, this is the App Store is not exclusive to Ubuntu, so it's running on Ubuntu, Raspbian, Fedora, and so on. You have you see like the list of some of the list of contributors to the store, and there are some examples of the applications that you can install. Everything packages a snap. Literally thousands of applications, and as I said, more and more ready for RISC-V. So what does it take to enable Ubuntu Core on new platforms? So we have two main snaps that we have to worry about. So it's a kernel snap, so think of it like a Linux kernel plus initRD plus your device tree, firmware files, kernel modules, all packaged as a one immutable file system. And then you have a board enablement package, what we call gadget snap. So that's all your non-HLOS components. So your bootloaders, if you have a trust zone kernel or whatever you have, untrusted firmware in ARM, Grab, Intel, whatever is your bootloader, U-boot, all that would go there. We have a bootloader configuration and we have a storage layout. So it's a description of your board. This segregation allows you to have one kernel snap that allows you to enable family of boards, and then you have a gadget snap per each particular board while sharing single kernel snap. So you can have easier maintenance for the kernel snap and reusability. Now, so enabling Ubuntu Core on a new platform, so we have tools that we use for that. So it's a Snapcraft, so it's a powerful and easy to use command line tool. So it use snap packages. It's supported on all the Ubuntu distributions. You can run it headless in a container inside on Ubuntu server. It's part of the CI. Ubuntu image, again, command line tool that allows you to build a final Ubuntu Core image that you can then flash to your board. So for that, all you need to do enable is the gadget and kernel snap. The rest of the system is coming from Ubuntu. We have kernel and all the other parts of the system ready for RISC-V already. Now we enabled the RISC-V already on QEMU as an example. There's a link to the GitHub repository, and we also enable it on Sciped Lychee RV, and that's this little robot here, thanks to my colleague here. And now we can go to before I will go to the demo, if you have any questions about it. So I'm here now SSHing, so I'm SSH'd in a QEMU. You can see that it's indeed RISC-V. And now we can look some of the snubs that we already have installed on the system. So you see that, for example, we also enabled LXD Linux containers on it, and I can demonstrate you that that is fully functional by jumping into the container and running. So we have Ubuntu 22.04 Jammy running inside a Linux container on a RISC-V. Isn't that cool? So we have fully enabled. You can, if you jump out, you can search the snap store. You can install additional snaps. You can play with it. Now, to go to the next demo, I can also show you that you have this. And that's a robot over there. So again, I can demonstrate you that it is indeed RISC-V. And we have a few snaps running here, which expose us the web interface. And we have a little robot here, which I should be able to control. So that's a robot running on a RISC-V, controlled by the RISC-V board.